Hello, welcome to the course on analog and digital communication. Dear students, in the last video lecture, we have discussed about scrambling process. Now in today's class, we will going to discuss about digital communication receiver. So before starting digital communication receiver, let's discuss about concept of AWGN channel. So what is channel? So channel is a physical medium which provides path for signal to travel from transmitter to receiver. Correct? So this is a simple role of the channel in communication engineering. Now we are going to discuss about the AWGN channel, special type of channel which is known as a AWGN channel. अब ये AWGN channel क्या है? तो बच्चों AWGN channel is the simplest channel model in communication engineering. अब ये AWGN का मतलब क्या होता है? तो the meaning of word A, that is meaning of this alphabet A, that is additive. W stands for white, G stands for Gaussian, and N stands for noise. तो ये AWGN वो बेसिकली एडिटिव वाइड गॉसियन नॉइस है, और जो चैनल ये एडिटिव वाइड गॉसियन नॉइस इंट्रोड्यूस करता है सिग्नल में, उसको हम बोलते हैं AWGN चैनल. अब इसका नाम एडिटिव क्यों रखा है? तो ये बेसिकली जो हमारा नॉइस है एडिटिव वाइड गॉसियन नॉइस, वो बेसिकली गॉसियन नॉइस है, और जब भी सिग्नल AWGN चैनल थ्रू ट्रांसमिट होगा तो ये जो AWGN चैनल है वो गॉसियन नॉइस इंट्रोड्यूस करेगा, और वो गॉसियन नॉइस ये हमारे सिग्नल x ऑफ t में ऐड हो जाएगा. x ऑफ t में क्या होगा? ऐड होगा. इसीलिए उसका नाम रखा है एडिटिव. मीन्स नॉइस एड्स टू द सिग्नल, हेंस इट इज नोन एज अ एडिटिव. अब उसको वाइट भी बोलते हैं. व्हाट इज द मीनिंग ऑफ दिस वर्ड वाइट? वाइट मीन्स द पावर स्पेक्ट्रल डेंसिटी ऑफ दिस नॉइस, the power spectral density of this noise is constant. The power spectral density of this noise is constant, hence it is termed as white. It is Gaussian. Okay, Gaussian means if I plot the probability distribution function of this noise, then it looks like a bell-shaped function. If I plot probability distribution function of this noise, then it looks like a bell-shaped function, and it is characterized by Gaussian noise is characterized by its mean mu, and variance sigma square. Mean mu and variance sigma square. Correct? Okay. And if I denote this Gaussian noise, then it is denoted by calligraphic letter N and characterized by two parameters. One is mu, another is sigma square, where mean is mu and variance is sigma square. So the variance basically defines the spread of this function. It defines the spread of this function, that is a variance, and mean is the point at which this function is centered, that is PDF is centered, probability distribution function is centered. Okay, and Gaussian noise is denoted by calligraphic letter N. This denotes the Gaussian, and it is characterized by its mean mu and variance sigma square. और AWGN चैनल क्या है? तो वो ऐसी चैनल जो एडिटिव वाइड गॉसियन नॉइस सिग्नल में इंट्रोड्यूस करे. और ये नॉइस कैसे अफेक्ट करता है सिग्नल को? सो बेसिकली दिस नॉइस सिंपली एड टू द ट्रांसमिटेड सिग्नल. सो रिसीव्ड सिग्नल y of t is basically x of t plus noise, that is the AWGN, additive wide Gaussian noise. Okay, and Gaussian is a basically a random variable which is basically its shape is looks like bell function, and its mean is mu and variance is sigma square. Correct? So this is the concept of AWGN channel. Now let's discuss about the digital communication receiver. So figure shows the schematic of digital communication receiver. So as we discussed, whenever we pass the signal x of t through the AWGN channel, then it will introduce the noise, which is the additive white Gaussian noise, okay, which add to the signal, and this is our received signal y of t at the receiver, and basically y of t is nothing but x of t plus noise n of t. X of t is our transmitted signal, correct? X of t plus n of t. N of t is the additive white Gaussian noise. Now this received signal y of t is passed through the filter, which is basically linear time invariant system, and output of this filter is r of t, and output of this filter is sampled at time instant capital T, where t is the symbol duration, and sample signal is r of capital T, and based on this sample signal the decision device will make the decision whether the received sample is 1 or 0, correct? So in this way the digital communication receiver will work. I repeat, the received signal y of t is passed through the filter, and filter is basically linear time invariant system. Output of this filter is basically sampled at time instant capital T, where t is the symbol duration, and from this sampled signal, that is r of capital T, the decision device will make the decision whether received signal is 1 or 0. Received sample is 1 or 0, correct? Now let's understand this functionality of this digital communication receiver mathematically. So basically this is our filter, that is h of t. Its impulse response is h of t, which is the linear time invariant system, and as we know, the linear time invariant system is basically characterized by its impulse response. So the impulse response of this filter is basically h of t, and as we know, whenever we pass any signal through the LTI system, then the output signal is nothing but it is a convolution of input signal and its impulse response. So simply the output of this filter, that is r of t, is equal to convolution of input, that is y of t, and its impulse response of the filter, that is h of t. So r of t is equal to y of t convolution h of t, where h of t is the impulse response of this LTI system or filter. And if I expand this convolution, then it can be written as integration minus infinity to infinity y of t minus tau h of tau d tau, and this basically represent the convolution operation. This defines the convolution operation. This is the convolution operation. Okay. So basically what we get, r of t, that is the output of this filter, is basically minus integration minus infinity to infinity y of t minus tau h of tau d tau. We also know that y of t, that is the received signal y of t, is nothing but x of t plus n of t, where n of t is the additive white Gaussian noise. Okay, correct? So y of t is given as x of t plus n of t, and x of t is our transmitted signal, and transmitted signal is basically given as, mathematically given as a0 p of t, where a0 is the symbol, a0 is the encoded symbol, and p of t is the pulse. Means transmitted signal is basically symbol multiplied by pulse, that is p of t. And what is the symbol? So basically we have the, at the transmitter side, we have the information bit stream like 1 0 1 1 0 1 and so on. Okay, and at the transmitter side what we are doing, we are mapping this information bit to the symbol. So suppose I map this 1 to minus a, let's say symbol minus a, and map this 0 to the symbol a, let's say. You can also map 1 to a and 0 to minus a. For specific scheme, let's map this 1 to minus a and 0 to a. So this 1 is again mapped to minus a, this 1 is also mapped to minus a, this 0 is mapped to a, 1 is mapped to minus a, 1 is again mapped to minus a, 0 is mapped to a. So this is the, these are the symbols, transmitted symbols. So A0 will be either minus A or plus A, and that is multiplied by the pulse, and that is our transmitted signal. So our transmitted signal is x of t is equal to A0 P of t. So if I put A0 P of t instead of x of t, then my y of t is equal to A0 P of t plus n of t, and replace this y of t in this expression, that is y of t minus tau. So basically यहाँ पे t की जगह पे मैं t टाउ माइनस टाउ कर दूंगा, तो ये मेरा y of t माइनस टाउ हो जाएगा, y of t माइनस टाउ हो जाएगा. अगर t को मैं t माइनस टाउ से रिप्लेस करूँ तो ये क्या हो जाएगा, A0 P of t माइनस टाउ प्लस n of t माइनस टाउ, और y of t माइनस टाउ को ये r of t के एक्सप्रेशन में हम रिप्लेस करते हैं. सो व्हाट आई विल गेट, r of t इज इक्वल टू इंटीग्रेशन माइनस इन्फिनिटी टू इन्फिनिटी A0 P of t माइनस टाउ प्लस n of t minus tau into h of tau d tau. So this is the output of the filter. Now this output is sample at instant time instant capital T. So the sample signal is given as r of capital T is equal to integration minus infinity to infinity A0 P of capital T minus tau plus n capital T minus tau into h of tau d tau. So what I did, just replace this small t by capital T. That is our sample signal at time instant t. Now if you observe this r of capital T, then it has signal component as well as noise component. This basically n of t minus tau, h of tau, basically noise component. So if I separate signal component and noise component, then r of capital D is given as A0 integration minus infinity to infinity P of t minus tau into h of tau d tau plus integration minus infinity to infinity n of t minus tau h of tau d tau, where this is the basically signal component. This is our signal component, and this represent the noise component. Correct? So this is our sample signal at this point. That is r of capital T. Correct? Now we have to discuss about this filter. So the question came into mind, what is this filter and how to choose this filter? How to choose this filter? So the question came into mind, how to choose the filter h of tau. So basically we have to select the filter such that it will maximize the signal power and minimize the noise power. मतलब जो signal power है उसको maximize करे और noise power को minimize करे. Ultimately, the filter should be such that it maximizes the signal to noise ratio, because what is SNR? It is a ratio of signal power to noise power, और हमें signal power को maximize करना है, noise power को minimize करना है. So ultimately, the role of the filter is to maximize the SNR. So we have to select the impulse response of the filter such that it will maximize the SNR. Okay, that is signal to noise ratio. So we have to select, or we have to choose this impulse response h of tau such that the signal to noise ratio is maximized. And in order to maximize the SNR, the filter response h of tau should be equal to the pulse, that is P of t minus tau. मतलब अगर filter का response, that is h of tau, is equal to this pulse P of t minus tau, then it will maximize the signal to noise ratio. It will maximize signal to noise ratio. Okay, and the filter which maximize the signal to noise ratio is basically known as a matched filter. उसको हमने मैच फिल्टर रखा है बिकॉज उसका इम्पल्स रिस्पॉन्स इनपुट पल के साथ मैच हो रहा है, इसके लिए उसका नाम रखा है मैच फिल्टर. सो द फिल्टर इन डिजिटल कम्युनिकेशन रिसीवर इज बेसिकली matched filter. The name of this filter is matched filter. And what is the role of this filter? The role of this filter is to maximize signal to noise ratio. It will maximize signal to noise ratio. Okay, so what we got after sampling? So after sampling, again consider this r of capital D is equal to A0 integration minus infinity to P of t minus tau h of tau d tau plus माइनस इंटीग्रेशन माइनस इन्फिनिटी इन्फिनिटी एन ऑफ टी माइनस टाउ एच ऑफ टाउ डी टाउ. और ये नॉइज कंपोनेंट को अगर मैं एन टिल्डा से डिनोट करूं, लेट मी डिनोट दिस नॉइज कंपोनेंट बाय एन टिल्डा, देन द सैंपल रिसीव्ड सैंपल at time instant t is given as r of t is equal to a0 integration minus infinity to infinity p of t minus tau h of tau d tau plus n tilde. N tilde represent the Gaussian noise. Basically this n tilde represent the Gaussian noise. Okay, and what is the Gaussian noise? So we know Gaussian noise is basically denoted by calligraphic letter n with mean mu and variance sigma square. With mean mu and variance sigma square, and its probability distribution function is basically bell-shaped function. It is a basically bell-shaped function. It is centered at its mean mu, and its spread is basically sigma square. So this is the variance of this Gaussian random variable. Correct? Okay. Now as we know, for match filtering, h of tau is equal to p of t minus tau. So for match filter, h of tau is equal to p of t minus tau. So if I replace this h of tau by p of t minus tau, then r of capital T is given as a0 integration minus infinity p square t minus tau d tau plus n tilde. And this integration minus infinity p square t minus tau d tau is basically energy of the pulse. This represents energy of the pulse, which is EP. Let me denote the energy of pulse by EP. So if I replace this energy of pulse by EP, then my received sample, that is R of capital T, is equal to A0 EP plus N tilde, where A0 is our transmitted symbol, correspond to either minus A or plus A. EP is the pulse energy, and N tilde is our Gaussian noise. N tilde is our Gaussian noise. And what is the Gaussian noise over here? Here this Gaussian noise has mean 0, has 0 mean, and its variance is equal to eta नॉट डिवाइड बाई टी EP. तो यहाँ पे जो Gaussian noise है उसका मीन 0 है, मतलब मीन इज 0 and its variance is eta naught divided by t EP. So the noise after sampling has 0 mean and its variance is equal to eta naught divided by t EP. So basically what we will get, R of t is equal to A naught EP plus N tilde. N tilde is a Gaussian noise with 0 mean and variance eta naught divided by 2 into EP. So R of t is basically given as A0 EP plus N tilde. Now as we know, A0 is basically transmitted symbol, and transmitted symbol correspond to either plus A or minus A, plus A or minus A. Correct? It is plus A or minus A basically. Correct? So as I said earlier, 0 is mapped to the plus A and 1 is mapped to the minus A. Okay, so correspond to this information bit, the symbols are A or minus A, plus A or minus A. So if you receive the plus A, then it will correspond to 0, and if you receive minus A, then correspond to 1. So the received symbol is either plus A or minus A. So the received sample is given as R of t is equal to plus or minus A EP plus N tilde. So we have two possibility. At any time instant, the R of t is equal to plus A EP plus N tilde if the symbol is A, and it is R of t is equal to minus A EP plus N tilde if the symbol is minus A. So these are the output after sampling. So we have two outputs, we have two possibility. One output is R of t is equal to AEP plus N tilde. This correspond to transmitted symbol A, and this output R of t is equal to minus AEP plus N tilde. This correspond to transmitted symbol minus A. Now if you look at this thing carefully, then this is the our Gaussian noise N tilde, and AEP is basically constant. A is the symbol and EP is the pulse energy. So A into EP is basically constant, and if I add constant to this Gaussian noise, the resultant quantity is also Gaussian. Resultant quantity also Gaussian. तो अगर आपके पास Gaussian noise है, AWGN है, और उसको इसके साथ आप कोई कांस्टेंट क्वांटिटी ऐड करते हो तो रिजल्टेंट इज ऑल्सो गॉसियन रैंडम वेरिएबल. तो n tilde is Gaussian random variable, and if I add some constant quantity to it, the resultant is also Gaussian random variable. ओके और Gaussian की एक इंपॉर्टेंट प्रॉपर्टी है जो मैं आपको बताने जा रहा हूँ. तो सपोज मान लो कि मेरे पास एक Gaussian रैंडम वेरिएबल है, उसका मीन म्यू है और उसका वेरिएंस सिग्मा स्क्वायर है. अगर मैं ये Gaussian रैंडम वेरिएबल के साथ कोई कांस्टेंट k ऐड कर रहा हूँ, कोई कांस्टेंट k ऐड कर रहा हूँ, तो क्या होगा, तो रिजल्टेंट क्वांटिटी होगी वो भी Gaussian होगी, लेकिन उसका जो मीन होगा दैट इज एडेड बाय कांस्टेंट k एंड वेरिएंस रिमेन्स अनचेंज्ड. वेरिएंस रिमेन्स अनचेंज्ड मतलब आपके पास Gaussian रैंडम वेरिएबल है और उसमें आप कुछ कांस्टेंट क्वांटिटी ऐड करते हो तो उसका जो मीन है दैट इज एडेड बाय दैट इज चेंज्ड, मतलब मीन इज इंक्रीज बाय दैट कांस्टेंट, मीन बिकम म्यू प्लस के एंड वेरिएंस रिमेन्स अनचेंज्ड. मतलब यहाँ पे वही चीज हो रही है. आप देखो, नोटिस करो, जो हमारा रिसीव्ड सिंबल है दैट इज आर ऑफ टी, रिसीव्ड सैंपल सिग्नल है दैट इज आर ऑफ टी, इज बेसिकली Gaussian रैंडम वेरिएबल n tilde दैट इज एडेड बाय कांस्टेंट AEP. अब याद करो, हमारा जो ये नॉइस है इसका मीन कितना है, 0, मीन इज 0, और उसमें हम क्या कर रहे हैं, ये नॉइस में हम क्या कर रहे हैं, कांस्टेंट AEP ऐड कर रहे हैं. मतलब उसका मीन 0 था, मीन इसका 0 है, नॉइस का मीन 0 है. ये जो नॉइस है L tilde उसका मीन 0 है और उसमें हम कांस्टेंट क्या ऐड कर रहे हैं, AEP. करेक्ट, मतलब इसका मीन क्या हो जाएगा, AEP. वेरिएंस रिमेन्स अनचेंज्ड दैट इज सिग्मा स्क्वायर. सो रिजल्टेंट R of t is Gaussian random variable with mean AEP and variance sigma square. Correct. Similarly, if transmitted symbol is minus a, then resultant, the received sample signal is also Gaussian random variable with its mean minus AP, minus AEP. Okay, minus AEP. So if I plot the probability distribution function of both this signal R of capital T, then you can see this is the Gaussian random variable, so its shape looks like a Bell function as I mentioned. Correct. और इसका मीन क्या है, that is the A into AP, so its mean is A into AP, and variance is sigma square. Variance remains unchanged, that is the sigma square. Similarly, if I plot the PDF of this R of capital T, then it has mean that is minus AP, minus A into EP, and variance sigma square. So this is the PDF correspond to R of capital T when symbol is minus A. So its mean is minus A into EP and variance is same, that is a sigma square. Sigma square. And this is the point of intersection of these two PDF, and point of intersection is 0 by the symmetry. By symmetry. Okay. So basically जो sample signal है that is R of capital T is basically Gaussian random variable with mean minus A into EP, variance sigma square for symbol minus A, and for symbol A it is a Gaussian random variable with mean A into EP and variance sigma square. ओके मतलब ये हुआ कि डिजिटल कम्युनिकेशन सिस्टम में आफ्टर सैम्पलिंग जो हमें सैंपल मिलता है, सिग्नल जो मिलता है, दैट इज बेसिकली Gaussian रैंडम वेरिएबल विथ मीन A into EP और मीन माइनस A into EP. Okay, now this is the received sample or sample signal at this point. Let me show you in the diagram. So this is the R of t, which is basically Gaussian random variable with mean A into EP or minus A into EP. Now how this decision device will make the decision based on this Gaussian random variable. So let's discuss how the decision device will make the decision from this Gaussian random variable which is R of t. So the rule is very simple, decision rule is very simple. So from this PDF, if received a sample, that is the sample signal R of capital T is greater or equal to 0, then it will define this area. It will define this area, R of T greater or equal to 0. This is the PDF. This is the PDF correspond to R of T greater or equal to 0. Okay. So if R of T is greater or equal to 0, then what decision device will decide? It will decide that the symbol is A0 is equal to capital A. Correct? Because this PDF is correspond to R of T for A0 is equal to A. Correct? So this is the PDF correspond to output R of T for A0 is equal to A. Okay, because इसका ये A0 is equal to A के लिए ये random variable है जिसका mean A into EP है. Similarly, if received as मतलब sample that is R of capital T is less than 0 in this area, then decision device will make the decision that A0 is equal to minus A. This defines this area. Correct? Okay. So decision rule is simple from this diagram. If R of capital T is greater or equal to 0, then it will decide that this PDF is existing. Means this is a PDF for A0 is equal to A, that is higher. Okay, probability of having A0 is equal to A is higher in this area. So the decision device will make the decision that the symbol is capital A, मतलब plus A. Similarly, if R of T lies in this area, that is less than 0, then the decision device will make the decision that the symbol is minus A. So very simple decision rule. If R of capital is greater or equal to 0, this will decide capital A. If R of T is less than 0, it will decide minus A. Correct? Because अगर R of T greater than or equal to 0 है मतलब this area, and this area is basically PDF for A0 is equal to capital A. And if R of T is less than 0, then it will define this area, it will lies in this area, and this area is basically PDF for A0 is equal to minus A. Okay, so in this way the decision device will make the decision whether the symbol is correspond to plus A or minus A. And as I mentioned, this symbol A correspond to information bit 0 and minus A correspond to information bit 1. Okay, clear? So what we discussed in today's class, we have discussed about the schematic of digital communication receiver. So basically the received signal is passed through the matched filter which maximizes the signal to noise ratio. The output of the matched filter is sampled at time instant capital T, and from this sampled signal the decision device will make the decision whether the received signal is information signal is 0 or 1. Received information bits is 0 or 1. Okay, so I hope कि आज के लेक्चर में जो हमने डिस्कस किया आपको समझ में आ गया होगा. Let's stop here. We'll discuss other aspect of this course in our next video lecture. Thank you very much.